How's everyone doing? All right, hanging in there, working, keeping it real. We're nearing the end, and as you know, there's so much left in this class that's still to be done. So maybe just take a deep breath. Okay, it's gonna be okay. It's gonna be okay. The airfoil lab is probably going to be pretty rough, but I think you're going to enjoy this, what we're going to talk about today. Okay. I think this is getting into mechanics, which actually numerically is more difficult, but in terms of the user interface and familiarity with mechanics, it's probably a lot more straightforward. Okay. So I hope that you'll enjoy the change of topic, the change of the physics for this class. You know, in terms of the stressors, all right, so we all took a deep breath. So now let's look at everything that gets to be done before the end of the semester in this class. The convergence checkpoint is going to be due, I guess, next Thursday at midnight. I'm going to give you the feedback on the demo simulation pretty soon. That one should be faster. There's still stuff I'm dealing with across multiple fronts, but even with the preliminary project outlines, the next assignment that you'll have as relevant to this topic that we covered today is about diving boards, and that will be due a week from Tuesday. So this Tuesday you're going to be airfoil assignment that's due, and then following that you have this one. Okay. It's maybe too early to talk about this, but we do have a room assigned for the final exam on May 12th. It will be in ARC 103. And that'll be from noon. Yeah, from noon to 3, if I'm not mistaken. Am I mistaken? Is that time, the finals time? I can take a look. Yeah. All right. So that's why you're in lunch. That can't be. All right. I'll get. But the room is assigned. The room is set. All right. Any questions, administrators? What we've been discussing. Any questions academically about what we've been studying? Intellectually, analytically. Somebody with me? No? Okay. Yes, Mia. Yes.
With the machine, could you do, instead of a space mesh, get all of the.
Like a what? Instead of, say that again, instead of a face mesh?
Instead of using face meshing, you can just use like a method.
Ah, okay, okay. So you definitely, I mean, a method is something you're going to, you could employ. In that case, I think I let it do its own thing, so it probably has a lot of quadrilaterals in it. Okay. There have been cases where you, I think even in this class, another instructor has not been as particular about the mesh itself and just let it do its own thing. The issue can be that your accuracy will suffer. Okay, you will get most likely you will get an answer. Okay, you will get something that will converge at least on itself. How it compares to ground truth might vary. Okay, so the reason that we do the layer meshing right on the surface of the airfoil was to satisfy the Y plus side. So in that case, what we saw is that the mesh right above the elements, right above the surface of the airfoil, had a height of something like 6.4 microns or something like that. And that satisfied, for the velocity we were considering, that satisfied the y plus value of 1, y plus value of 1. So because at that interface between the surface, the hard surface, and the air, there's a gradient in the velocity, and so you want to capture that. So often we put a lot of elements right there. That was a long-winded answer to saying maybe. Okay, maybe. Other questions? Okay. Well, let's go back to mechanics. And we'll review the nomenclature, some of the ideas behind statics and mechanics with statically loaded structures. We will also just throw out the equations that are being solved, and that would maybe be enough to say, oh, this is pretty complicated, we'll find an element to solve. And then we'll talk about cantilever beam and axial loading on a bar. So in terms of reviewing, this may be a familiar slide. Okay. Just maybe it's not. If you took mechanics materials with me, this is one of the ones that we've used. The basic idea is that structures have loads, and often before you took mechanics materials, you were really just thinking about the external loads. But then once you took mechanics materials and statics, you're like, oh, there are internal loads, there are internal forces, there are internal moments, there are internal stresses. So the basic idea is you slice it, you dice it, and you look to see what the stresses are, how those forces are distributed over cross-sectional areas. And then we can shrink down those cross-sectional areas. So we get these traction forces, and we shrink down the cross-sectional areas and make them small, and we can get traction vectors, and we can then get to stresses. Okay? So these would be maybe traction forces, and then we say, hey, look, we can define these traction vectors, not traction forces, traction vectors, as a composition of different stresses acting on a face, like that. Okay. And you're familiar with the nomenclature that we use. We have sigma xy, sigma yx. But do we really say sigma yx? Do we really say sigma xy? No, right? We usually use tau for our shear stresses. And we use sigma x for sigma xx, sigma y for sigma yy, and sigma z for sigma z. Okay. So when was the last time that you did mechanics? I'm just wondering, like where you are, when was the last time you wrote sigma x, sigma y, sigma z? Yes, Josh?
Maybe that measurement slot.
Okay, so that's happening now for you, or?
Last semester.
Okay, when was the last time that you wrote down mechanics equation? I'm just wondering, yes, here.
I'm taking aeromats and aerostructures, so all the time right now.
All the time right now, all right, yeah, okay, all right. You've got some good stuff going on with those wonderful people, all right. Yeah, anyone else? So, okay, you're taking aerospace materials and aerospace structures. Anyone else? That's not an aerospace engineer. Or I'm just curious. When was the last time you wrote, sigma equals E epsilon? Huh? Measurements. That was so. Some of you are taking measurements now or not? Everyone. That's all last semester. Yes.
Mech props.
Yeah. Okay. So with Professor John.
No, psychological.
Oh, it's different. Okay. All right. Cool.
Well, no, activists both teach it, like, depending on what section you're in.
Okay, all right, good. Sorry. Yes. Okay, so you could have. Yeah. Okay, good. And you're raising your hand.
I was
Yes.
just saying there's both.
Oh, okay. Well, behind you. You know what I'm saying? DMC, all right, what's up? That's a fun class too. Okay, so good. So it's not like you've completely forgotten mechanics and materials. No one said the last time it was mechanics and materials. That's a good thing. So your understanding has augmented since those good old days. All right. So these slides should just kind of be refreshers then of how we look at the equilibrium and the conventions, right, that we use for shear stress. If we have a 2D element, right, if it's positive, if it's, and in quote the positive direction, we have the tau xz going to the right and tau zx going this way. Tau xz, tau zx are the same, those elements. Otherwise, it would be rotating or moving if we didn't have all these shear stresses on these elements. Okay? Good. So that's the review. Actually, not quite. There's still more. Actually, let's go back yet. You remember also that we could use equilibrium in many cases for the determinant problems to solve for the stresses. Okay. And we went through all of statics. I'm hoping that in statics that we will get to adding more about stresses. But we went through all statics, being able to solve equilibrium from internal forces, internal moments, right? All those moments had to be determinate because you didn't know about material properties yet, right? Remember, the indeterminate properties required knowing something about how deformation was involved in boundary conditions, and then using the elastic moduli to be able to figure out, okay, it's an indeterminate problem, I have to do more, I have to look at the constitutive relationships, right? So these are the constitutive relationships that we were typically interested in and using for a linear elastic material. Where are the V's? All right. Well, this equation, all right, and it can be put in matrix form, okay, or you can go the other direction as well. All right, you can go from the stresses, you can go to the epsilons. All right, so we've got our stresses and we've got our strains, okay, that we're interested in using to be able to at least looking at axial loading and seeing how this corresponds, what the relationships are. You also have situations where you have shear stresses. Okay? And if you have shear stresses, you can relate the shear stress to, just like sigma equals E epsilon, right? We said that sigma can also be, or tau, at least for the one direction, can be related to the shear modulus times the shear strain. Okay? So you've got this idea, all right? I think at some point, and this is how it was taught to me when I took the equivalent mechanics class my sophomore year, and used this book, that you could kind of break your piece of paper into 3 columns if you want. I don't emphasize this too much, but I did talk about it some in the class. You have your equilibrium column, you have your geometric compatibility column, which is really the boundary conditions and how displacements work out. Often you hope that they're going to be 0. And you have the constitutive equations, right? So for like a 1D linear elastic bar, right, your constitutive equations would be the sigma equals E epsilon. And I've said that multiple times, but of course if you have multiple dimensions, then you have to also consider the Poisson effect, right? How the material is shrinking under tensile load. Fun time. Elastic modulus of aluminum. What? 70 gigapascals, right? Okay. Steel. Someone else. Not there. Because if you know one, you know the other one pretty soon. Pretty easy. Yes. Yeah, 200. So it's roughly about 3 times that of aluminum. Poisson ratio of steel. Poisson ratio of aluminum. Poisson ratio of many metals. Yes.
0.3.
Yeah. 0.3. 0.3 is a good one. 0.23, 0.2 something 3, yes. Any other materials you want? You guys quiz me. I'll try to give you one on the right order of magnitude. Okay, what? That's a good one. I'm gonna say probably around, say around 10 gigapascal. No, what is it?
I don't know.
You don't know? Okay, so fact check me here. Fact check me. All right, I'm quizzing you, quiz me now. Someone tell me what's the elastic masses of copper?
110 to 130 gigapascals.
Copper. Elastic modulus.
Young's.
No, Young's modulus is 110?
Yeah.
Huh?
I also checked it. Well, it's 110 to 130.
Okay, so I'm off by order of magnitude. All right, give me another one. I'm embarrassed myself on that line.
Silicon.
Silicone? Oh, that's all over the place. But you can have some stretchy silicones. That was like a given. You know I like silicones, right? All right, so you can have some that are super stretchy, like that are 10 kilopascals, and it can go up to and then it can go up to about 1 gigapascal maybe. But it's more like usually it's more like 10 megapascals. Or 1 megapascal. All right, that was nice. Thank you. Yes.
Rubber.
Silicone is a rubber. So, but rubbers can vary quite a bit. You could it could be 100 megapascals or so. Depends on the hardness. Yes.
ABS.
Woo! Okay, that one I'm gonna go around 1 gigapascal.
Close. 1.8 to 3.2.
Take that one. All right. Any others? Okay. The Poisson ratio for many of these rubber materials is also around 0.5. But when you put it in simulation, don't use 0.5 because that would cause the simulation to explode. So what you usually use is around 0.49 in simulation. Okay. All right. So this well, actually, maybe in aerospace structures and aerospace materials, we might cover these relationships in the differential form. Okay, but this is not like a requirement. The point here, okay, is just that we, again, can break numerical problems or numerical implementations of problems into a set of differential equations that are across the 3 domains. Okay. Of what are the 3 domains? Equilibrium, geometric compatibility, and constitutive relationships. Okay. So we don't usually in mechanics materials we don't introduce these scary equations. Okay. But you can see resemblances to what we just discussed. For example, the strain displacement relationships, those are still there for a linear elastic material. Okay. You've got this idea of F equals ma for equations of motion, that's equilibrium. Okay. So the V is the body force, acceleration is A, and that goes to 0. Okay. You've seen some of these compatibility relationships, but these are based on geometry. Okay. And so what happens, and the point here is just to say, this is not the Laplacian of U. Okay? Right? So for heat transfer and stuff, right, where we're looking at Fourier's law and the heat equation, essentially that was a Laplacian of the temperature, right? Is equal to the flux, or is equal to 0 or equal to something. Actually, I'm messing it up now. Sorry, don't quote me on any of that. You have Fourier's law, flux, change in temperature with respect to displacement, then you have the heat equation. So it's complicated. So the actual solving using the finite element method, okay, is more complicated. The idea is still that you could use the Lurkin method. You can still use this principle of, hey, I have a K matrix and a temperature matrix and a forcing matrix, right, that you have in the invert decay matrix, still all in place, right? And we're not, this is even more impressionist than what we usually do, okay? And we're just gonna say that it's even more complicated, okay? And we're not even going to do it, not even going to try, okay? And the same principles apply though. You can use different shapes, you can use different order elements. So like, if you say, you know, I've got a triangular element, but I am only going to allow for linear relationships. So like in this, where did we go? Oh no, come on, you can do it. Okay, good. I'm only going to allow for a linear deformation on that side of that face, of that triangular element, or on the edge, right? That's going to eventually be faster to solve when you have a bunch of these elements, but it may be less accurate. Okay, so what happens is sometimes you have these mid nodes, and you could have lines there, or you could have a mid node, like you could have a line there, or it could be a second order, so you could have a curve in that mid node. Okay? So there are a lot of different elements that you can use to, one, fit into the geometry you have, and then two, as the deformation evolves, to capture that deformation. And if you're doing a project that involves this involves structural mechanics, that's fine. Just keep in mind that you can also demonstrate convergence by increasing the number of elements in nodes, just like you would in any other problem. And this is just also more about that. You know, you can change the relationships, the basis functions, like that's essentially what we're talking about in terms of what are the possibilities, what can you fit between these different elements and different nodes. Okay, and here are the equations. If you so desire, some of them have one approach, I guess, to being able to do these types of simulations. Okay, so we're going to go back a little bit to mechanics and materials world. A little bit different. I didn't think about this much or give you much of a warning, but if you're in a few minutes, we will do a little bit of Ansys, and if you would like to follow along and you have a computer or you have access to the remote server, you'll be able to, you can join us if you like. It's not a requirement. Just thought that if you want to, you can, because I think it'll be pretty easy to follow along in a few minutes. Okay, so plane stress, plane strain. What's the difference? What's the game? All right, plane stress, plane strain. You tell me. You remember? Okay, so what's the difference? Yes?
Say the question one more time. I didn't hear the second.
What's the difference between plane strain and plane stress? What was it between plane stress and plane strain?
Well, both of them are in plane, which means we're only looking at 2 dimensions. And then plane stress refers to the amount of force happening over a certain given patch of that plane. Plane strain, meanwhile, is the proportion of displacement that plane undergoes.
Okay. So that's an interesting idea that you're connecting, yes, the strain, the definition of strain and the definition of plane stress. Okay, that's good. That's good. So in the case of plane stress, all right, typically what we're saying is that the stress in the direction of the board is 0. Okay. All right, and this therefore, and it also means that we're assuming that these are thin sheets. In the case of plane strain, okay, what we're saying instead is that the strain in the board is 0. Okay. And so typically in that case, it's very thick. Okay. Think of it as more of a plate type structure. Okay. So just in terms of what we did in mechanics and materials, we usually thought about more circle in terms of what's happening in plane stress. Okay, remember that? And then we cover plane strain a little bit. And we think about what's happening with more circle and strain with that. And then we kind of use some assumptions about plane stress and flip them around for plane strain. Okay, but the idea here is that these two situations are distinct and allow us to make 2D simplifications when we're trying to solve for the stresses of concern. You know, going back, why do we even care about measuring stresses? Now, this is kind of, at this point, you're like, oh, yeah, I know why. Actually, maybe yes. So why do we even care about calculating stresses? Yes?
So we don't go past the yield strength of material, or like the breaking strength of material.
Right, so one is failure, all right, and one is yielding, and then we have the ultimate strength as well, and we also have, I know about fatigue, because you can DMC, right? So failure, that's one reason. What's another reason we take care about stresses? It's also related to functional requirements. So you're essentially, one of your functional requirements is don't break. Otherwise, it's what you want to use. What's another functional requirement? Maybe we ask the question, why do I care about strains? What's my other functional requirement? Yeah?
You don't want to like overly long. You don't want to pass a design length or something.
Yeah, so you've got another set of functional requirements related to how much displacement is involved. Wait, what? I missed what was funny.
No.
Oh, okay, all right, good. All right, so we're all right. Yeah, so these are some of the reasons why we care about this. And when you're doing your simulations, it's good to know, okay, which situation am I really thinking about in terms of, do I expect there to be plane stress or plane stress? Plane stress or plane strain? Okay, this is something that Professor Singer emphasizes quite a bit, and this is something that if Professor Singer were writing the final exam, I talked to him a little bit about it, this would definitely be on. Okay. For me, it's you gotta know something about this, but it's not gonna be quite as safe. Alright, so we're just gonna review, and so you should know this. I'm not saying don't listen to me, I'm just saying it won't be as big a component. Okay? But it will be a component. Alright? So this slide is kind of bare. It doesn't exactly get everything across yet, because we have to think about something. So in particle dynamics, what were our options for boundary conditions? And what was kind of one option we had for symmetry? Okay, so all right. What were our options? Yes, we're completely, we're talking about structures. Look, structures is at the end of this list, all right? So we're going to get into this like a little bit of reflection. What were our boundary condition options, and what was one symmetry that we talked about? Yes. Oh, wall. Good. All right. Oh, wall. All right. Which is both a boundary condition and a symmetry. Alright? So Professor Singer's emphasis is that this is a hard wall, and an angle of incidence equals angle of reflection. Okay, that's true. Okay. So we have some angle here, right? We could have a particle running parallel that has the same symmetry. Okay, so that's one. So hard wall, boundary, and symmetry. And of maybe less important, what was the other boundary condition we introduced? We did a lab with it. Yeah, that thing, yeah. The periodic boundary condition, right? Okay. So the idea was if you have a wall, you have another wall, right? And your particle goes through it, it comes out over here, right? So you have the periodic boundary condition. Okay. Heat transfer. Boundary conditions, symmetry. Yes?
Adiabatic.
Okay, so yes, adiabatic, good. What does that mean?
Use Q
Yes.
0.
So this is insulation. Means Q equals to 0. And this would be a form of a, what type of boundary condition? You got two. You have two. Pick one. Be bold.
Usually.
The other one. Okay, good. All right, so that's one. Okay, and so in terms of, so this is our BC, our boundary condition. All right, and one way to kind of think of this from a symmetry perspective, so a insulative BC is also akin to symmetry. Blah, 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 blah. Okay. So if, for example, you have temperature over here, and then you have a wall, and you say this is insulating, okay, you can say that this is a symmetric. Wait, no. Yeah, we can say this is you've got this boundary, and so the heat is being reflected right back at you. Okay, and so this is reflecting, and it is insulating. So reflecting heat. Okay, and then what's the other one? You have the Dirichlet, right? And this is going to be a case where you have a specified temperature. Temperature is equal to a constant. It could be equal to 0, but more likely it's going to be equal to a constant. So you should have adiabatic insulating, right? This is Neumann. This is a specific type of Neumann, I should say. So specific type. Because you can also have a fixed constant. just like you have a Dirichlet boundary condition. And in this case, there's not really symmetry. It's more that this is the temperature here. You're specifying, right? And you have all your nodes as well. Okay. With fluids, what are the boundary conditions that we typically think about? It's one that everyone loves to say. Yes?
No slip.
No slip, okay? So no slip, which just means that the velocity is equal to 0. Okay? What's the other boundary condition?
Shear.
Okay, what about it?
No shear.
No shear, okay? So the other one is no shear. Okay? So you might want to take your own notes so this is clear, all right? But you can, whatever. So no shear is a boundary condition and also a symmetry. Right? That's really bad looking. Okay. How is it symmetric? Well, if you had a flow, let's say, moving along here, right? We know that the flow is going to be exactly the same on the other side. Okay, so this is kind of like a symmetry or a mirror, if you will. And so this is the same kind of thing. This is kind of a mirror as well. And this is kind of a mirror as well. So that's what we have in fluids. Those are our boundary conditions and our symmetry. Okay, what about structural mechanics? Well, for structural mechanics, you can think of this situation where if you have, for example, like plane strain, you have a lot of material on the other side. Okay. And you can think of this as essentially being a frictionless boundary between them. Okay? So in this case, what's happening is if you have a bunch of stresses and you have a bunch of strain on one side, the stresses and strain are the same. So this is a symmetry, and I think this one's a little bit of a stretch, to be honest. But anyway, this is and it's not necessarily super intuitive, but this is how you can think of a boundary between different regions of a fit material. So, if Professor Singer asks you, okay, tell me about the symmetries in multiphysics, you have a list, all right? The list would be, well, we have mirrors where you have no shear in fluids. You have kind of this mirror or the reflecting boundary condition in insulating case for heat transfer. And we have a symmetry or a hard ball or a mirror, all the same thing, in particle dynamics. Okay. And then if you have boundary conditions, I guess the boundary conditions in structural mechanics, though, I should cover that. Typically, we were saying that you have some type of force being applied. Or you have a moment being applied. Okay. Or you have a fixed condition. Okay. Or you have a free surface, which would be kind of similar to this idea, okay? Except you have a boundary and there are no instead of saying, oh yeah, that same forces, same stress, the same strain are applied on that side, this is a free surface. And so the air, and so the stress in the air, the strain in the air is 0. Any questions? Pause for discussion, for thoughts. Insights. Do you disagree? Do you agree? I think the boundary condition, I think the symmetry idea can be argued a little bit in the structural mechanics. Yes?
Just, can you explain the Dirichlet boundary condition one more time?
Yeah, Dirichlet is, remember where we had conditions for specifying temperatures at the walls? That is Dirichlet. Okay? Those were the fun ones. Those were the easy ones when you look at the differential equations. Neumann was more of a pain, to be honest. Right? But Neumann comes from Fourier's law. Okay? Yes, Mia.
Would you say that vibrations would be periodic?
Okay, so vibrations. You're saying vibrations?
Yeah.
Okay, so we will cover vibration a little bit the next time we meet. All right, there are nodes and antinodes and periodic patterns that will form, okay, on a structure, just like if you have a string vibrated. So it's periodic in that way. I hadn't thought about it in terms of like an overarching idea that vibrations or have symmetry. Yeah, but definitely you have waves. If you have waves that are present in vibration for sure. Okay. And there are different types of waves, right? There's the compressive waves, so for acoustics, you have more compressive waves. But then we often use what we think about transverse waves in mechanical structures. Well, actually, I shouldn't say that. There are people who think a lot about compressive waves in structures and surface waves as well. Good. Other thoughts? Ready to move on? Okay. All right. So, ductile material. It's kind of here, but which criteria, so more than one, would you use to analyze the potential for failure, mechanical failure, or yielding with a ductile material, a ductile structure? And let's go back. Name a ductile material first. So first, what's a ductile? Name one of your famous ductile materials. Yes?
Rubber, I guess.
Okay, rubbers, okay, ones that we use more in structures. But rubbers, yes, for sure. Yes?
Copper.
Okay, copper, yeah, that's a ductile one. Yes, Ian? Steel. Depends now on the type a little bit, but yes. Because steel is made of iron and carbon, right? So if you have cast iron, for example, which is not really a steel, I guess, then that's going to be in the brittle category. But yes, many of the steels, most of the carbon alloys that we're dealing with are ductile. Even though you're like, wait, is that really true? Yes, it's really true. How do you remember that? You remember the necking, right? When you pull the ductile piece of steel, right, and it necks, that's ductile. Whereas if it's a brittle material, it goes boop, and it leaves a little nice little bumpy surface. Aluminum is another ductile material. Okay, so now we have some ductile materials in our minds. What are the criteria that we use? Two that we cover mechanical materials. Yes.
Are you looking for failure criteria?
Yes.
Okay.
I'm looking for failure criteria. But you're in aerospace materials and aerospace structures. So that's good. Go ahead. So just celebrate. Right? I am the interviewer, willing to pay you a lot of money on an annual basis, and I ask you this question. So your answer is
What?
no pressure. Go ahead.
Mises or Hashi, right?
So von Mises, yes, and we just usually call, what's the other one that we call mechanics materials?
Max stress.
Which max stress?
Kanika's answer for
Huh?
That's the other term I removed from.
I can't remember.
No, it's on the screen. Stress test, alright? So maximum shear stress, alright? Remember, you could calculate out on a Mohr circle very easily the equivalent maximum shear stress, at least for uniaxial or 2D. Alright? Actually, even also for 3D. Okay? If you knew the principal stresses, remember that? You could draw 1, 2, 3 circles. Alright, and you draw a big circle around the biggest circle you can draw, and that's going to be the one that tells you the maximum shear stress. Alright? It's important though, okay? If I have uniaxial loading, everyone's thinking, oh, you know, I just gotta know the yield stress. If I know the yield strength, boom. But if it's for aluminum or steel, is it failing because of the maximum? Is it failing because of the stress in the normal direction? No. It's failing because you have a maximum shear stress that happens to be related to a yield strength, okay, for a ductile material. Okay? Because remember, there's these things that they call the Luder lines at 45 degrees, okay? And there's like slipping. You can see it in some tests, where that slipping corresponds to a shear stress, and the material is actually shearing, even though it's under normal stress. Does this all sound familiar? Okay, so now, the way to calculate the maximum shear stress is not too difficult. It's the principal stress divided by 2, right? And you can do it from Mohr circle. The von Mises stress criterion has to do with looking at maximum deformation. You may remember this a little bit, and in 2D you have this like sigma y squared equals sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared at the bottom. But more, you were calculating equivalent. Okay? And so in this case, this is nice for 3D. If you know the state of stress, how many for a linear elastic isotropic material, right? You have sigma x, sigma y, sigma z, tau x, y, tau x, z, tau y, z. You have 6 parameters. Okay? So if you know those 6 parameters, boom, how useful is it as an engineering tool based on actual physics and mechanics to calculate von Mises stress? That's very nice. So what's going to happen a lot of times is you're going to click on, whoops, give me the von Mises stress, and that's all you're going to think about. Okay? Hopefully you'll think a little bit more. Is this a ductile material or not? Is this, is it fair for me to use this criterion? Okay. And how does this stress, right, relate to the actual normal stresses that I have? You can tell, right, you see, if I have uniaxial loading, it comes back out. So uniaxial loading, what does that mean? That means that I have sigma 1 and sigma 2. Sigma 1 is equal to some value. Sigma 2, sigma 3 are equal to 0. Okay, so if sigma 2 and sigma 3 are equal to 0, that means I have a sigma 1 squared here, and I have another sigma 1 squared. Okay? But the other things, and so I get 2 sigma 1 squared here, all right? And 2 divided by 2 is 1, so then I get, it's the same thing as in the actual. So just to give you a little bit of a reminder of what's going on. All right, so now if you have gotten your Ansys up, if you want to, you don't have to. Okay, we're going to attempt to look at some problems here. Okay, and the geometry we're going to put into space-plane is going to be one where we have a height of, well, so the height here is 0.5 centimeters, so 5 millimeters. The span is going to be 30 millimeters, or 3 centimeters, and the length is going to be 15. Okay? Alright, I'm just clicking around here. So we haven't done this before, but we're going to look at using static structural analysis. And so we bring it in, and what we'll do is to go ahead and put in the material properties for what we're interested in. So let's see, what did I put here? What did I put here? Did I put them in? Oh, okay, here we go. We're going to do 200 gigapascals for steel, and then we're going to put in a thermal coefficient of expansion of 6 times 10 to the minus 6. All right. So let's come out here and double click on engineering data, and you could say, oh well, maybe I should just use structural steel because I like structural steel. That's fine. We're going to add a new material, and we're just going to call it our material. And then we can come over, and we're going to say it's a linear elastic, so we can select isotropic elasticity. Oops, I have to drag it over the property button. Okay, and then I can click on this, and we can go ahead and put in our elastic modulus, which is be 200 gigapascals. And we can put in 0.3 for the Poisson ratio. Yeah, okay, come back over here. We can also give it a density. Anyone remember the density of steel? Right, anyone remember? Yeah. Huh? 7,000. Yeah, 7,800 is what we're going to use. Okay, good. Very good. Do you remember the density of aluminum? Yeah. No, okay. Technically, we don't necessarily need to put a density in, so I'm just putting it in. I mean, if you do gravitational loading, you need it for sure, okay? But the mechanics formulas are not going to do it, but I'm not quite sure, I can't remember if Ansys will behave nicely without density or not. Okay, so we're going to put it in. And we don't have to put in a coefficient of thermal expansion if we're not doing a heat problem, but we're going to do a heat problem eventually. All right, so here's the isotropic coefficient, okay, isotropic material, coefficient of thermal expansion. We're going to say it's 6 times 10 to the minus 6, and that's times 1 over Kelvin, right, so Celsius, inverse Kelvin. Inverse Celsius. A nice thing to remember to do is to right-click over here and go ahead and make this the default solid material. So our material is now the default, because if you're like me, sometime you'll run a simulation and you'll accidentally just end up running it with the default material, which is steel. Okay? We're actually going to do 3D, so don't worry about changing that. Let's go ahead and right-click again. Yes, and we're going to do spaceplane here. And our dimensions, while that's coming up, are 3 centimeters wide, 15 centimeters long, and 5 millimeters tall. And also we'll have 10 kilonewtons as the force that's being applied. Okay, it still says it's starting. All right, so then, yeah, I'll click on the Z and we'll draw things in this plane. We will go ahead and do a rectangle. And we said that it was going to be 150 millimeters. Right, so 15 centimeters. And we said that our span would be 30 millimeters. Okay, so that should be good. And then we can come over here. Actually we'll go ahead and end the sketch. And we can do a pull. So this comes, and then while I'm pulling, it shows a number, and then my right hand's on the mouse, my left hand is still, I'm still holding the mouse button down. Okay, doesn't matter if you're left-handed or right-handed, or right mouse or left mouse. Okay, 5, enter, okay, and that's our geometry. That's it. We close this, our geometry's in, and then we bring in the model. We bring it into the modeler, which is where we're going to mesh. So, any questions up to this point? Fun? Boring? Less boring than normal because at least you have like a video of things moving around. Okay. I hope it worked. You might want to, okay, well, down on the bottom, down over here, and jumped around, you do have the opportunity to select your units. We're working in millimeters, so that should be fine. I'm a little surprised by what's happening here. What we will do is add an axial load, okay, through this member. Now, maybe now's a good chance, though, while we're waiting, to just run a couple calculations. So here, what's the first thing I might be interested in calculating is the axial stress. So in this case, sigma x is going to be equal to what? It's the sigma 1, so it's the force divided by the b and h. So the force that we are applying is 10 kilonewtons. So we have force is equal to b over h, and we're applying 10 kilonewtons, and it's over what is it? 3 centimeters and 5 millimeters. So I believe the answer is 67 megapascals. Let's just check with our famous Google method. Okay, so we said it was 10 kilonewtons divided by 5 centimeters times 3 millimeters. All right, and I can say in MPa. All right, so 67. Okay. All right, are you back? Oh my goodness. That is not happiness. Buenas noches. All right. Very disappointing. Very disappointing. I'm gonna try it again. That's probably a bad idea. Is it a bad idea? Am I going to get fortunate? I don't think so. Oh, whoa. Okay. Hey, maybe I should buy a lottery ticket. Okay. I can't believe that worked. All right, so just make sure that we have only one solid, all right, which is what we have. Make sure that we're using our material, okay? So this one is being assigned to body 1, so that's good. All right, and we can come in here and we can mesh things. So we'll go ahead and in this case we'll just insert a sizing, and for our geometry we'll select the whole body. So we select, hit apply, and then for element size, the default I think is too large. And so let's just see what it looks like. Sorry, mesh, here we go. All right, too large. I mean, yeah, actually, for our type of problem, it's probably not that bad, okay? But we can do, without much effort, we can do better. So if we put in 2 millimeter, we generate. Okay, that looks a little bit like it would capture interesting behavior. Okay, now, we need to add some boundary conditions, right? So we said that we're going to put a force axially on this, like that. So that's going to be apply, and we said that it's going to be 10,000 newtons. What happens if I run the simulation right as it is, right now? What do you think happens? Well, let's find out. Oh, it even tells me it's smart. Not enough constraints. All right, if I apply 10 kilonewtons on one side of an object, it's going to accelerate quite nicely. Okay? So what do I have to do? I have to add some constraints, right? Now, the normal thing that I would do, and it's actually not even just normal, this is what you should do in many cases, all right, is to go ahead and put a fixed constraint, fixed support on this face, like that. All right, and that's fine. We'll go ahead and we'll get some information about deformation, about, oops. What am I doing? Ooh, this is interesting. It's not. Sorry, solution. I was clicking on the wrong one. We'll get some. I don't know. Let's see. We'll say maximum principal. That's fine. Stress equivalent Vormesi's. Sure. Stress maximum principal. Yeah, that's the one we just calculated. And it's uniaxial, right? So that they should just be the same. Okay, but we'll go ahead and we'll run the simulation, then we'll talk about that boundary in a second. So it's building the model, and we go back over here while we wait. It shouldn't really be that long, but we said that the actual stress should be 67 megapascals. If I want to know the deformation, let's say deformation, right? Remember the equation for deflection of a Oh no. What just, not having a good day in terms of computer working. Okay, so sigma, for, yeah, delta. Oh, come on. Okay, was equal to PL over EA. Remember that one? It's blast from the past. Okay. So let's take a look. If we come over here and we go to the result, we can click on this probe. When we click here, boom, 67. 67. All right. So. That was not planned, 100% not planned. I've used this number, 67, for like 3 years, okay? Not planned. And I also just broke a vow with my kids that I would not say that anymore. All right, so Alright, anyway. Shoot. And that's so sad. That's the only time you'll clap for me all semester. Alright, so anyway, the equivalent stress, alright, the maximum principal stress is 67, like we saw, megapascals. If we want to come over and look at the equivalent stress, okay, that should also be the same number, okay? Now, one thing that was kind of interesting, and you can see it here, that there are values of different stress. And it may be more clear, nope, that's not the best. That's not the best. Yeah, that's not bad, okay? Why do you think that the values are not completely light blue? Why are there variations in the stress near the left side? Sure. Okay, what were you gonna say? Yeah, go ahead, Kevin.
Displacement.
There's what?
Displacement.
Okay, yes. So it wants to displace. In which directions? It wants to displace because there's a Poisson effect, right? It wants to displace inward in both the z direction and the y direction, right? Because I'm pulling myself a problem that you would just get accelerations, and that would be unhappiness. So what you can do, if we really want to make it look like a textbook, is we can suppress our fixed support, all right, and now everything's like, oh, you just changed me. Yes, I did. Okay, and we can insert a displacement constraint on this side. All right, now which direction or directions should we fix? If I want like a textbook, I want it to look completely uniform there. I'll give you a hint. If I fix all three, it's exactly like a fixed support, all right? So in this case, I'm going to add, and I'll give you another hint. I'm going to add another boundary condition in there. So which way for displacement would you want to keep it fixed? I just said that it wants to deform in the y and the z, right? Should I let it deform the y and the z? Yes, because I want it to look just like a textbook, where it's all nice and uniform. Okay, it depends on which textbook it is. Mechanics and materials textbook. Okay. So I'm going to fix it. Right now they're all free in all three directions. I'm going to fix it in x. Okay? So it can't move in the same direction I'm applying the force. Okay, so that's by putting it 0, okay? And I'm going to add another boundary condition, a fixed. Okay, I am going to add a fixed support, but now I'm going to add it only at the corner. See, so I'm selecting that node. So just that node is going to be fixed in that direction. That means it won't allow everything to slide. Well, it's not going to move in the x direction, and it allows all the neighboring particles to slide in the x and the y direction, but that one spot is what's fixed to the real world. Okay, so that's there. I don't want a face. No. I want fixed support, and I want it on a node. On a vertex, sure. Well, actually, maybe I'll just do it on a node. I'll do it on the node, like this. There we go. One node. Okay, that was weird. I don't know. Maybe it would have done it if I had applied before. Okay, so now, if this works, and I've had issues with this not always working. Invalid geometry. Okay, so that's what it's doing. It doesn't like that. Let me see. Do I need to do it on a vertex instead? Okay, it says it's on a node. The displacement, oh, that's why, Toowoomba. That one needs to be on a face. I didn't hit apply. Okay, now we should be good. Okay, in a minute, we'll also apply, okay, it's fine, it can be large, I'm okay with that. Okay, but let's take a look at what happened. Okay, so deformation, it actually does show that there's some slight deformation, okay, overall there is some, okay? That's kind of strange. But the equivalent stress across the whole thing, or the maximum principal stress, is 67 megapascals across the whole thing, right? So that's because it's letting it move, all right, in those other two directions, and I still have one point that's fixed to the ground, but my displacement is not allowed to go in the x direction where I'm applying the force. So that's kind of fun. Now let's go ahead and we're going to suppress this. Actually, I guess I don't have to suppress it. Yeah, I'm going to suppress it because I'm going to do something else. I'm going to use this and I'm going to unsuppress. And I'm going to suppress my force. Okay, it's like, whoa, okay, now what do I have? I have no load on anything except I have a fixed support. So if I solve this, everything should be zeros. Okay, it says I need at least one structural load. All right, fine. I'll put in well, I don't have to put a very small force to show you. All right, what am I going to do now? Well, another type of problem that you can solve, if you remember from mechanics of materials world, is a thermal problem. Okay, so I can look at the thermal expansion. So I've prescribed this coefficient of thermal expansion here. And to do this, I insert a thermal condition, okay, and let's just put 100 degrees here. And for this, I'm going to select the whole body. Okay, it's doing this the whole body, great. Oh, of course, I have to select it. Okay, now apply. So that's applied to the whole body. 100 degrees Celsius relative to what? Well, I should probably take a look at the environment temperature. Okay, so it's 0. And I think that is essentially, yeah, that's all I have to set. So now we'll have a temperature differential of 0. And then if we look at this, and if we come over here, there are a couple things. So if it's free, right, then what I would say is, okay, what is the strain in the axial direction? Well, that is just going to be alpha delta t. And if I want to know the change in the length, right, then it's going to be the epsilon x times L, or alpha delta t L. Okay, and in this case it was 100. So 100 times 6 times 10 to the minus 6, so that gives us 6 times 10 to the minus 4 times 15. 6 times 15 is 90. So 90 times 10 to the minus, well, that's 15 centimeters. I have to do all the units right, but let's just see what it tells us. Hopefully it's got about a 90 somewhere in there, or a 9. All right, so let's look at the total deformation. Boom. All right, it says that the max is 0.091 millimeters. Okay, so that's correct. I think it's correct. And then if I wanted to look at the Okay, so now if I fix both ends, what kind of stress do I get inside the bar? I don't allow it to expand. What's the stress going to be inside? Don't give me a magnitude, just I want to know what type of stress it is. Yeah, here.
Can you compress it?
It's going to be compressive, right? This is going to be trying to expand, right? And then it's not going to be allowed to expand, so it's going to be in compression. So if we now enable that fixed support that I had disabled right here. No, wait. Okay, actually I think I need to add another one. Because this was at a point, this is the displacement. Okay, let's add one. Here, on this face, apply, and let's run it. Okay. So in this case, we would get, let's see here, whatever the string, right, we can say, oh, this is more or less uniaxial, so it would be the stress will be the strain, right, times the elastic modulus. And that was something like 6 times 10 to the minus 4 is what we said it was. 6 times 10 to the minus 4, elastic modulus is 200. That's like 12, and then I got 10 to the 9, and then I got 10 to the 9, and 10 to the minus 4. Or, so that's, what's 9 minus 4? That's 5, right? So that should be, let's see, should like maybe 1.2 megapascals? I'm not sure. Let's see what it comes out to be. Okay, my math was wrong. Or no, maybe, no, it wasn't. Hold on. Yeah, my math was wrong, okay? But this is, the stress, I'm surprised it's varying that much. Is this stress? Interesting. Well, let's see what the equivalent stress is. Ah, no, so I said 112. I said 1, okay. So now I like, this is interesting. Why is the maximum principal stress? Because you have Poisson effect as well. All right, so the Poisson effect is having, is like you can see, the Poisson effect is significant here. Okay, as it's, because it wants to constrain it. It wants to expand in that direction as well, but it's not allowed to. So that's, but the equivalent still comes out to be something like 123 megapascals, which I think makes sense. I said it was 12 times something. Just a note, this is not real. What is not real? This deformation that you're seeing. This is scaled by 640 times. Okay, the auto scale. So sometimes you want to say true scale, and then you can't see it. Okay. So just be aware that the software will often like expand and do things like that. All right, so in the homework, oh, we're over time. Okay, time flies when you're having fun. All right, in the homework, there will be something about an impact factor that you will get to remember, I hope, from your DMC days. And let's do the attendance. Thank you, everybody. I feel like a collective relief that we're not doing CFD anymore, but maybe it's just me. I could be wrong. Maybe I'm the one that feels surprised.